in this lecture and the next couple of lectures, we will discuss and go to some extent in detail the physics and technology of semiconductor spin qubits. The discussion will be confined to quantum dot spin qubits, which are realized on semiconductor systems. So, when we discuss qubits, let's first overview what makes a qubit. Start with the classical bits first. Okay. So, let's go laser pointer. Okay. So, we know that all the technology or processors or computers or chips what we use currently are based on classical logic and classical bits, or simply you can say bits. So, basically these bits are basically transistors. They are basically with the MOSFET geometry, or you can also have other kind of storage systems where you can have two opposite magnetization direction of a ferromagnetic domain. That also makes a bit. Like you have an on state and off state for a transistor, or two polarization directions or two magnetization directions of a small ferromagnetic domain. That can be a storage device. We can also have transistors such as MOSFETs, CMOS, okay, to store and manipulate information. So, when we call the bits, mostly we refer to a MOSFET device where you have a channel which is either turned on or off depending upon the gate voltage that you are going to apply. That's a bit. So, this is basically a bistable or two-state classical system. When we talk about quantum bits, those are also two-level or two-state quantum systems. I'm not going to go in detail what the details of this quantum system that we will discuss in a minute. Assume that there are two states, but the difference here is you can also have a state which is a combination of these two states. When I say combination, it's a superposition of these two states. So, for example, the 0 state is pointing up and the 1 state is pointing down. If you take a linear combination of these two states, A and B are in general complex numbers. So, that state can actually point in any direction in this unit radius sphere. That is another state which is as good as 0 or 1 state, but that is not a possibility when we discuss classical bits. You have only two states, 1 or 0 or 1. That is it. This combination or any intermediate state is not a defined, well defined state, but in this case the intermediate state is also a well defined state. And how we use this quantum state in a computation, or how we exploit this quantum behavior, is all left to how we manipulate these states and how we write an algorithm to certain computation. Those details we are not going to discuss in this lecture. This will be mostly confined to discussion on the technology and basic physics of these qubits. All right. Now, let us look at what is the basic difference between the quantum computation and the classical computation. Assume that you have a computer with n bits. So, that will give you 2 to the power n minus 1 states. Okay. But for a classical computer, these are well defined states, well defined zeros and ones. So, there are these 2 to the power n minus 1 states. All these states are available to you, but only one at a time can be addressed, or one at a time is possible. So, when you do a computation, this is a normal process flow. This is just a very primitive description of what are the different steps involved. You start with your system with all the states certain pointing in certain direction, or they are all initialized to certain states, say zeros. Then when all the states are 0, the probability of all the states are 0 is 1. That's a definite probability. I would not even say probability, that's a probability is 1. It's a definite state. Then during the computation or during the process, these bits will be flipped, manipulation of the states are done. Then at the end, of course, there will be an intermediate state where some k state, the probability for the state is 1 again. Okay. K is just a index. Okay. Now, the final result is a state P of A out of this 2 to the power n minus 1 state, and that is what you are going to get, and that is also a robust state with the P of A is equal to 1. That is the normal process flow. But when we look at a quantum computer, these are states with a defined probability. For example, the state of system which consists of which is defined as a linear combination of all these states. They are all there together. For a classical computer, you have these states, but they are all not together. They need to be addressed one by one. All the states are not available simultaneously, but here the state of system is a linear combination of all the states with the coefficients a's. Square of that will give you the probability for that state, how much of that state is there in the total. Okay. So, again here you will initialize the system. So, you set everything to say 0, P of 0 is psi 0 squared. Now, we are talking about wave functions or state vectors. Here also you have 2 to the power n minus 1 amplitudes. Here you have 2 to the power n minus 1 states, and the stark difference here is the states can be accessed simultaneously during computation. The state of system is a combination of all these states. Okay. And computation is nothing but a time evolution of the state, which is, but what sequence or what way it evolves, that depends upon the algorithm, or what are the process, what are manipulation that you are going to do, okay, or how the system is going to evolve. So, there will be some kind of intermediate state, but overall probability will be 1. That means psi n squared at any time, the modulus of that will be 1. And eventually the result, that is will be a state where the probability PA is maximized, or the algorithm will work in such a way that eventually you will be able to measure the final state with a probability PA, that is given psi A square. So, that is the process flow for a quantum computation, but the difference here is these states, all these 2 to the power n minus 1 states are available to you in classical computation, but they are in sequentially, they are in sequence, like that means it is available only one by one. Here the state is a combination of all that state, all those states, and you are accessing all these states together, they are all connected. The state of system is superposition of all these states, that is the difference. Just to give you a feeling of what extra power that this is going to give you, consider you are trying to solve a puzzle which consists of a maze, and you are trying to find a way out starting from here, how will you reach here? So, classically, or what you do when you get a puzzle in a magazine or in a book is you try different paths. For example, you try one of this path, okay, that didn't work, you go back, try again a different path, that didn't work, then eventually and sequentially you will find the right path down. That is what you do. These individual paths are addressed separately, but if it is a quantum maze, the state of a system or the evolution is basically kind of parallel. I should not say parallel because it is not a mirror parallelly following all the paths. The state of system is superposition of all these paths. So, you are accessing all these paths simultaneously. Okay. It is not just superposition, these paths are also quite often linked, they are entangled. So, the superposition principle and the entanglement, these two things together give quantum computation that extra muscle power, which makes it much superior to the classical computer for various jobs. So, the difference here is, as I mentioned in the previous view graph, the paths are addressed in a classical computer sequentially. So, you have to go through all the paths, but here this state of a system is a superposition of all the paths. You are accessing all of them together. Okay. So, all the individual paths can be in a superposition state, and the right path can be found using something called quantum parallelism. That is the difference. This is just one example. Okay. Now, we just discussed that the bits, whether it is a classical bit or a quantum bit, those are two-level systems. So, quantum bits or qubits are quantum two-level systems. Just to give you a quick overview for this, what are the different two-level systems that is familiar with us is a Bohr atom, where you have various energy levels, E0, E1, there are various levels are there. You can confine your workspace or parameter space to the first two levels, the ground and the first excited. You can assume the ground state is 0 and the first excited state is 1, and you can make a transition between these two states using an appropriate radiation source with a energy h bar omega equal to the energy difference between these two states. That is one example. This lowest two levels, confined to the lowest two levels. Another example for a quantum two-level system is one of the familiar problems in chemistry, the ammonia molecules, where you have two configurations depending on the torsion angle given by this and this. They have the same energy, but two configurations. So, the system can flip back and forth between these two if you provide a photon with appropriate energy. Okay. So, 0 and 1. This is another example for a quantum two-level system. Then spin states, those are pure quantum mechanical entities which does not have any classical counterpart. The spin states of isolated donor nucleus in a host material, say phosphorus in silicon, or you can have the electron spin, isolate electron spins in a host material such as gallium arsenide or silicon or any other semiconductor. So, spin down state and spin up state, you can have one as 0, one is 1. So, there is a 0 state and there is a 1 state. These are two states, and you can make the transition between these two states by supplying a radiation with appropriate energy, which equals the energy splitting between these two spin states. So, these are some very general examples for a quantum two-level system. Now, the question is, can any quantum two-level system, in short TLS, make a qubit? So, what are the criteria? What is the requirement? How do you select a candidate to be a prospective qubit host, a prospective system to host a qubit or a quantum processor? So, for that we need to have some insight into what a processor consists of. So, you have your basic unit. In this case, what I am referring to is a classical processor first, then we can make parallels from that. So, that is the knowledge that we have, how a classical or everyday processor is made of, and we can draw parallels from that and see how or what are the requirements to realize a quantum processor. Only those systems or qubit realized on those systems will be promising to make a large processor which consists of hundreds and thousands of qubits. Okay. So, what we have here is a classical processor which we start with a single transistor. This is a FinFET. We have source, drain, and the channel is looking like a fin. So, which you can see here. Okay, source and drain is a fin, and the gate actually wraps around the channel. Okay, and this is a array of these FinFETs. There are a lot of other circuit elements are there, such as interconnects, high frequency lines, powering lines, all kinds of things are there, which I am not going to go in detail. And eventually, you will end up with a processor to address all of this. So, a quantum processor eventually need to have all these things. You need to have a basic circuit element, a bit akin to the transistor. Then you need to have an array of these transistors which you can address individually, because you need to initialize all those things. We probably need to read out the states of many of these. Okay, we need to power this, control this, manipulate this individually. So, the scalability is a important criteria, because it's not having 1 or 2 qubits assembled. You need to have thousands of these very uniformly, arranged on a chip or on some kind of a platform. Then you should be able to access these individually, read out these states. You need to come up with an architecture, something like this, and eventually a processor. If you consider all these things, in late 90s, DiVincenzo put forth certain set of basic requirement criteria which a system need to satisfy to qualify as a qubit candidate. Over the time, this criteria has got refined. We are not going to go in much detail, but let's discuss the important parameters. The ability to address qubits individually, because you should be able to initialize it, address it, flip the bit, whatever you want to do during the computation. So you need to have individual access to these states. Okay. You should be able to initialize individual qubits, perform 1 and 2 qubit operations, and at the end of the cycle, you should be able to read out the final state by a single quantum measurement, because the measurement itself is going to decohere the system. So one measurement, you have only one chance, you measure it and you get the result out. And last but not the least, the decoherence rate. The decoherence is something which you are not really worried about in classical system, because it's a robust system. We need to worry about classical noise, and as long as the state is robust, it's fine. But it's a quantum system, is superposition, the coherence between different states need to be maintained. The state need to be maintained. Any disturbance can actually disturb the system, can damage the state or destroy the state. And the state decoherence rate or the decoherence time should be long enough so that the computation can be performed with a fraction of the coherence time. So you need to have very small decoherence rate. That is a really, really important criteria. Okay. So we have now kind of put forth what are the requirements, and our discussion after this slide and next slide will follow how the topic of this lecture and the next 2 lecture, the quantum dot qubits, satisfy these criteria, so that it is considered, so that it will be a potential and one of the front running qubit candidate system. Okay. Now let's look at what are the candidates, what are the leading candidates. These two are, the first two are ion traps and optical traps, where you trap ions or atoms and use the quantum state of these ions or atoms to do computation, store and manipulate information. These two are kind of close cousins. A lot of the technology they share, and they are very promising candidates. And when it comes to scalability and the and also solid state systems such as a wafer, a chip, these two systems, superconducting circuits and quantum dots, are very attractive, because you can use a lot of the CMOS fabrication technology currently the industry pioneered to make this system, make these qubits. Because we get a lot of help from the industry, because they are very familiar with processing this material. Okay. The architecture for these two are very similar. So scaling these bits into large scale, get a large processor with hundreds of thousands of qubits is relatively easy, because the industry has already figured out how to put billions and billions of small transistors on a square inch area. So, superconducting circuits which exploit charge or flux degree of freedom of Josephson junction devices, that is the leading candidate. And our topic of discussion is quantum dot, where spin states of isolated electrons in semiconductor quantum dots. So, this is an illustration where somehow you create traps, but which are regular. These are not randomly distributed traps, randomly distributed charge traps. These are regular, man-made, artificially created, controllable traps, defined electrostatically. The details we will discuss, okay, in this lecture or the next lecture. And you can get an array of these electrons, and you can use the spin states as we discussed in the previous one of the previous slides, spin up and spin down states of each of these electrons to define the qubit. And that is the focus of our discussion. So, what we discussed so far is there are few leading highly promising candidates, and the spin state of electrons in quantum dots. These electrons are confined to a very small region, and that is the quantum dot. That spin states of these electrons, up and down states of these electrons, are highly promising and attractive candidates for storing and manipulating quantum states, or they make good qubits.